Well, I've been hard at work working on the presentation I got to give for the FamilySearch Developer Conference on Thursday. So I'm pretty much done. I have some minor cleanup. I have a few slides that are bothering me a little bit and maybe want to add a few things. I may need to cut a few things. 25-minute presentation. Yee. We'll see what happens though. So I'll just go through it really quickly. Well, maybe 20, 25 minutes quickly, but we'll see it. Timer starts now. So the tree problem, an overview. So first of all, is it really a tree? You know, come on. It's not a binary tree. Let's stop calling it a binary tree. You have multiple sets of parents. You have divorces. You have adoptions. You have foster. You have multiple marriages. It's kind of a graph, and a mostly acyclic, mostly directed graph. So please, no more trees. So we're, graphs. Public versus private. It would be really nice if we could have stuff that's private and stuff that's public and be able to transition between the two and invite people to participate in our private stuff. To have both for our data, for what we choose, not just, oh, this stuff is private and this stuff's public. You can't do anything about it. We should be able to choose what's public and what's private. Disagreements. You clobbered my father, prepare to die. We should be able to disagree in a collaborative genealogy software program. We should be able to say, okay, on these 99.9% of the stuff, we agree, but on this one point, I don't think so. I'm going to see mine. I want to see what I believe. You want to see what you believe, and we go on our way, and we're fine. Should be able to support that. And a couple other things I also want. I want to be able to run my own stack. You know, as nice as it is to have an online stuff, I want to be able to run it locally. I want to be able to do what I want. I want and need proper performance and scaling. Let's just say that really doesn't exist right now in any public APIs, and desktop stuff doesn't run on servers. I want to be able to do expressive ad hoc queries. I want to be able to query my data, and I want to figure out what I want to figure out. I want to query it the way I want to query it. I want raw access. I want to be able to run online and offline. I want to be able to do both. So I'm actually going to skip kind of the why I ended up going with a graph to potentially solve this problem. Some of you read the roots dev stuff. I went into it a little bit there, but needless to say, it's a good fit. So here, a property graph is a collection of nodes, relationships, and properties. So we have A goes to B, goes to C. So we can store data in there. So A has size of 3 and is not cool. B has size of 5 and is cool. C has size of -1 and 99 lives. And edges have properties as well. So taking that, we could actually naively start relating persons to each other. It's kind of a good natural fit. We're going to go into more of this later, but needless to say, we can fit stuff in there. We can even do persona things. The sources point to personas, which point to persons, and that type of thing. We can model that. We can pretty much model whatever we want to. There's some really good existing property graphs out there. Neo4j, Titan, Tinkerbell's Blueprints does some abstraction through Java to let us access a lot of stuff. There's also many, many, many more that are out there. So vgraph. vgraph sits on top of a property graph and is a distributable versioned instance of a property graph. So it extends, think of it as an extension of a standard property graph. So we have a regular graph directed, and we add UUIDs to everything. So every node and every edge has a UUID v4 associated with it. Then what we can do is we can say, let's partition this into multiple repositories or multiple sets. So some can be public, some can be private. We can go ahead and partition. Arbitrarily, whatever we want, we partition. So 1, 4, and 5 are in red, 2 and 3 are in blue. If we look at the edges of those, when we're looking only at red, we have some we call boundary nodes that sit outside of our repository as kind of a marker that, okay, this node belongs in that repo over there. Because an edge must always be connected to two nodes. That's how it works. So A and D are actually considered within the red repository, and nodes 2 and 3 are boundary nodes. Now from blue's perspective, A and D are also in blue. And nodes 1 and 4 are boundary nodes, and blue does not know about 5. There's also some interesting things you can do when you have this case, and you have the edges being referenced in one without the other, which means you can go one way but you can't get back, which allows some really nice functionality when you come to kind of standardized stuff. But maybe remind me to talk about that if you're interested. So we can look at it. Our graph. So we kind of have a key on the side. Green is added, yellow is changed, red is deleted, and purple denotes kind of a boundary node. So we take our graph, we go ahead and make changes. We just add a node. Then what we do is we commit. And our commit, the information that we capture in there looks like this. Oh, we added this node and whatever properties happen to be associated with it. So now our graph looks like this. We'll add an edge. Now when we add an edge and make a commit, you can't send just the edge. What you send is the edge and boundary nodes, so that if you apply this commit to another graph, it knows that those two nodes are in our repo. If you do it in another repo, it comes to ours. Now we have our graph, and we're going to go ahead and update one of our nodes, add a new node and a new edge. Here's what we look like. Node's easy. The edge and the other node are added, and we have a boundary node. Again, so if you can apply a commit to any repository. Now we have a graph that looks like this. We go ahead and delete an edge. Now, when we delete, it's the same thing as adding an edge. We end up with two boundary nodes that exist for that delete. That may not actually be true, but we'll come back to it. So we have our graph there. Note, I got to change that if that's actually not true. We have our graph. We go ahead and delete two more nodes. Now, when we delete a node, all of the edges associated with that node are also deleted. So we come in like this. Now, a couple notes. You cannot edit boundary nodes. Boundary nodes mean that the information contained there is in another place. You're not allowed to touch it. Now, every single node has a label that is immutable, which means you know what type of node that is before you go, which means when you're doing a traversal, you don't necessarily have to go to that repo to figure out what you want to figure out. You only go there if you want to. An existing boundary node that's added to a commit points to the original repo. So if I do an edge, if I connect an edge to a boundary node in my repo that this boundary node points to repo A, I'm in repo B, I apply this to repo C, that boundary node still points to A. It doesn't do this weird transitive property thing, it points to the original. So in there, decap. So we're storing and querying vgraph commits. So what we do is we have this version layer, this commit layer, and when we commit, we get this commit object back out. And we can take that commit object and we can patch our repo. We can also do a clone, which is kind of it's a commit without changing anything. It just sucks stuff out. Now, those commits need to go somewhere. So we store, we query them. So the first thing, we have a decap store. We want to retrieve them by ID, date, author, repo, the nodes that are included, etc. Elasticsearch is beautiful for this because all of our nodes are actually JSON objects or representations, nodes and edges, and commits. An interesting thing is a commit may exist in more than one store, and that's fine. You can have a store in my machine and a store in the cloud, whatever, and that you can do that because commits, their IDs are also UUID4s. You have a decap server that exists, so it just sits on the top and provides a RESTful interface. The spec is language agnostic. All the commits are JSON, which means you can implement this in any language. You can do it in the browser, you can do it in Java, you can do it in Swift, whatever you want. And we also have a decap client. The decap client handles routing. It figures out, okay, when I need to save a commit, where do I send it? Do I send it to my local store? Do I send it out to another, something else elsewhere? What do I do with it? It also handles retrieval. So if you want to know, okay, I need this commit, it will take care. It's best to say this commit from this repo because it knows where to go get it. It'll go get it from that repo's commit store. If it doesn't, it'll query all the stores and say, okay, who's got this commit? Where did this thing come from? So an example deployment. We have on the lower left a Java server with a Postgres store and a Java client saving stuff there. It's saving itself out to this Elasticsearch store fronted by a Node server. We've got an Android client there. We've got a Swift client running on iOS. It's hitting our Java server and the Node server. We have JavaScript client hitting the Node server. Multiple languages, commits are flowing, everything's happy. So that takes care of the commit side of things. Now, endpipes. We need a way to query not just in our repository, but across repositories. That's what endpipes is for. It's a cross-repo graph traversal framework. It's modeled after Blueprint's traversals, what used to be called pipes in Blueprints 2. It's now called graph traversal in Blueprints 3. They did a giant refactor. So what it allows us to do is, follow a path in a particular repo, hit a boundary node or set of boundary nodes, and take that query and continue it on in another remote repo on a completely different server, in a completely different language, if we so desire. And then it continues on and it goes. And there's some things that allow us to restrict how deep it goes and to restrict how much time it uses on the cluster and some other things like that. We don't have time to look at this, given the shortness of this presentation. If you want to talk more, let's talk after. And I'm still working on this. I've got proof of concept there. There's still some things to work out, but it's fun. It's cool. So we can query, we store commits. Now P-tree, we need to know how the heck we store our data. And you got to store your data in a standardized way so your instances can communicate with each other. We can't just be throwing nodes and edges willy-nilly and clobbering labels and bad things happen. So what we do is we have a person. Now, we're person-centric. We're also kind of everything else-centric. But a person is a node with no attributes. Person is just a marker. It's a starting point. And a person is surrounded with all these conclusions. Names, birth, death, marriage, a whole bunch of events, anything you can think of, gender. Those are all conclusions about this person. So we can actually enter in at any conclusion point, get to the person and continue on. And the person, just a unique identifier. Just an identifier. There's no crazy nesting. There's no insanity on that person. No properties. So a birth looks something like this. You have three people associated with it. You have the child, the father, and the mother. Now this is biological. You also have non-biological kind of birth events. I'm not into the legality of them, but we can model them fairly easily. We just change this to, we call it something different, and you have parent, and then child, similar to how adoption works. So you have this birth, and this birth has a date and a place. So marriage is very similar, person, spouse, date, place. Now, you'll notice, first, properties. So each node has a list of properties associated with it. Date has an original date string and a formal date string, borrowed from JetComX. I actually implemented the Java end of that, so that was fun. Place has a name, some other stuff. Conclusion, based on the type, has multiple properties, and an edge has properties. So why did we make everything first class? Why aren't we nesting this? Why aren't we sticking everything under everything else? Why do we push everything up to the top and associate it? We get more granularity in versioning, sharing, and referencing. It means that everything has a unique identifier, even the sub pieces of this. This date for this marriage has an identifier. which is incredibly useful when you want to point at something. It's globally unique, that thing. It allows us a lot of more expressiveness when we query. I don't know why I'm looking over there. I don't know. My audience is over there maybe. Who knows? I should look at the camera. More expressiveness when querying and searching. It allows us to start at any of those first-class citizens. I want all names that will look like this, or I want dates between this range, and then starting there, I want to find dates that relate to conclusions that are in this place, get all of that set, and then go out to the people associated with those. And we can do queries like that. We can do searching. It's also much more extensible when we add custom elements and properties. So if I want to add some custom node, I just namespace it correctly. We'll talk about how extensions work in a little bit. Namespace it correctly, reference to the person, or whatever other piece of the model we want. And Bob's your uncle. You just included your own custom, essentially, specification or element, whatever you want to call it. So, as fun as that is, we've only dealt with what's. So what is like what happened or what was. A person was born, they lived, they died. They're typically called conclusions or facts in other systems. Those are completely separate in P-tree from why. Now, this is why you believe that a particular set of what's happened. Personas, sources, or notes are all examples of why you believe something happened. And those are completely separate concepts. And they're connected together by these why connectors. So you have this what graph that exists, and on top of it you have these whys. And these whys reference the what's and say, okay, this source with this persona and this collection of stuff supports this person, this date, this relationship, this parentage. Completely separate. And we do that because we can have multiple types of whys that support the same what. And the multiple types of whys support different types of research methodologies. You want different research, doing research different ways? Fine. Absolutely okay. You namespace them. They reference through the whys. You see the what. So when you're looking at a what, you say, oh, look, we have a why. We have a why that's persona. We have a why that's a note. We have a why, and we continue on down. It also lets us share all of that information. So the what's, I don't have to know exactly how to display the whys, but I can display the what's. I can just show what happened without worrying about why I think it happened, although it is extremely important. And another cool thing is you can create whys before you commit to creating what's. It's beautiful. I can create personas, create them, reference them, have partial references into the what graph without actually creating a what. I can say, well, I think it's this, between one of these two. And you don't have to ever create a what if you don't want to. So, P-tree, it's micro-standard based. You remember back here where we have a birth and a marriage, you have things like gender. These are specs. These are standards. There's micro-standards made up in part of a larger standard. If you want like Bob style names in your thing, fine. We can create a standard around that, and it interconnects and it plays nicely with everything else in the ecosystem. And it's built on vgraph, which means you get commits, versioning, all the benefits there. You get decap, and you get endpipes, which means you can query it. You get everything else, everything in the ecosystem. You don't blow away people's stuff. You can share. You can also experiment. You know, we can have a set of flags. It goes through. So that's Trepo. So what I just told you is Trepo plus a REST API. So there's a REST API that sits on top of endpipes, P-tree, and decap. And those talk to vgraph, which sits on top of a standard property graph. So Trepo is distributed. Because of the way it works underneath the covers with the partitioning into different repos, you can split to scale, and property graphs, there are linear scaling property graphs in terms of Titan. and some other projects. I'm not sure if OrientDB is. Trepo is extensible. You can extend ptree. You can modify, store any data you want within these graphs. Scalable. This thing will scale partially because you can suck it down locally and operate on it. You can put it up in the cloud. You can you can make it bigger, you can make it wider, you can do whatever the heck you want. And it's cross-platform. The specs for vgraph and everything else on top of it are language agnostic. Based around JSON, distills down to a property graph, and we specify exactly how you operate on that graph given everything. And it works in different languages. I create my initial one in JavaScript. I'm working on the Java one right now. They interoperate. They're interoperable. And Trepo is open source. Everything I've done is licensed under MIT, except for the logo for Trepo, which is like Creative Commons by attribution or something, whatever. But everything is completely open source here. You want to take it, you want to run it, you want to build a business on it, whatever the heck you want to do, you can do it. That's Trepo. Okay, I'm going to end this. It feels like I've been going for a long time. I have no clue how long I've been going. But it was fun. Found a couple points I need to fix. I'm going to go back, fix those. I may run this again tomorrow. Not quite sure. But yeah, it'll be a fun presentation. They did cut it down from 50 minutes to 25 minutes, which is why I'm kind of stringing this a little bit. But that's it. Take care.